So as a quick recap of our energy unit so far, we started by talking about work. And the reason for this was that energy is the ability to do work. That's one way it's often defined. So to understand energy, we have to first understand work. Then we started talking about energy itself, and we talked about kinetic energy and potential energy, specifically gravitational potential energy in this course. And we talked about how to calculate those two things. Then in the previous lesson, we tied it all together by talking about the law of conservation of energy, which I said is really the main reason why we study energy. Kinetic energy and potential energy on their own, they're fine. But where it becomes really, really powerful as a tool and really, really interesting from a cosmic perspective is when you look at how they play together and how energy is conserved throughout the universe. So that last lesson on conservation of energy was, you could say, kind of the most important lesson in this unit. The next couple lessons are going to be on two little ideas called power and efficiency. So these ideas are not as important as the law of conservation of energy, which is something that governs our universe and is of utmost importance to academic physicists everywhere. Power and efficiency are two little ideas that are used quite a lot by engineers. So more than sort of rules that are useful in determining how our universe works, these are little tools that we often use when we're inventing or when we're designing things. So first of all, today's lesson on power. Power is defined as the rate at which work is done. So just like we defined energy in terms of work, energy was the ability to do work, we're defining power in terms of work. It's the rate at which work is done, how quickly work is being done. So you can maybe guess from that the equation for power would have something to do with work and something to do with the time it takes to do that work. And indeed, the equation for power looks like this. It's the work done divided by the change in time while that work was being done. As with all of our equations, we're going to look at the units here. So work, as usual, we're going to measure in joules. All work and all energy is measured in joules. Time is going to be in seconds. And that means power. Well, if power is work divided by time, then the units of power are the units of work divided by the units of time. So joules divided by seconds, or joules per second. And as we're becoming accustomed to, a lot of these really important units we tend to rename. So the unit of 1 joule per second was used a lot and studied a lot by a guy with the last name Watt. So we have renamed a joule per second to a watt. One thing you got to keep in mind here now is we've got a couple of different W's floating around. There's this W here, which is a unit and means watts. And there's this W here, which is not a unit. It's a symbol that represents work. So there's W for work and there's W for watts. You got to keep those sort of straight in your head. And one way to kind of help you figure it out, if the W you're looking at appears in an equation, it probably means work. If the W you're looking at appears after a number, it's probably a unit, and it means watts. And then the tricky thing is that watts is not the unit for work. Watts is the unit for power, work as units of joules. So there's two W's, and you got to make sure you keep them straight in your head. Now, the way I like to introduce power to students is this. I say anyone can do a certain amount of work if you give them enough time. But power is actually worth bragging about. And to illustrate this point, I'm going to show you guys this photo here. So this guy's got a barbell, and he's probably lifting it up. And when I think of stuff that's worth bragging about, I often tend to just think of weightlifting. So what he's ultimately doing here is he's taking this weight and he's lifting it up to, I don't know, maybe this height up here. Now to do that requires work. Right? The weight has some potential energy here. It's going to have more potential energy up here. And that difference in potential energy is the amount of work you'd have to put in to lift it. So no matter who picks this weight up, if they're going to lift it from here to here, all those people are going to have to do the same work. Here's the thing. An ant could get this much weight from this level to this level. If I broke this barbell into a million tiny pieces, scattered them out on a table at this height, and then there was a little ramp up to a table at this height, the ant could piece by piece take every single bit of that barbell and get the entire thing up to this height. So the ant could easily do that much work. Frail little old lady. If you put this on the ground, this barbell, and you gave her a nice, long, gentle, easy ramp, she might be able to slowly roll this thing up the ramp and get it up to this height. So she could also do that same amount of work. This guy, our ant, and that little old lady would all be doing the same amount of work as long as they lift the same barbell, the same height. What this guy's going to do that's a lot different from the ant and the old lady is he's going to do it quickly. And that requires a tremendous amount of power. So although all three of them might do the same work, this guy is going to exert way more power because he's going to lift it up there much faster. Now, if you really look into this, there's a few things that make what he's doing more difficult. In order for him to lift this at all, he needs to have be able to exert quite a bit of force. And the ant and the little old lady wouldn't have to exert that much force to do their method. He's also lifting it straight up, whereas they have normal force sort of helping them. But you could also think of us as comparing a number of different weightlifters. Let's say we get 10 guys to all do a squat with this on their backs, and they're all able to do it. But imagine one guy whose kind of knees are shaking and his body's twitching, and it takes him 10 seconds to slowly inch this thing up, 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 and finish his squat. Whereas maybe another guy comes along and boom, in 1 second, without even grunting, he lifts it up. Although those two weightlifters did the same amount of work, the guy that did it faster is clearly a lot stronger, clearly has a lot more power. So like I said, power is actually worth bragging about, whereas doing work is something anyone can do if you give them enough time. So let's tackle an example here. Lover's Leap is a 122-meter vertical climb. I'm talking sort of rock climbing here. I actually think there's a number of climbs around the world that are referred to as Lover's Leap. I'm talking about one in particular that has a record time on it that was achieved at one point by a guy called Dan Osman. And so he did this rock climb in 4 minutes and 25 seconds. What is his average power output during the climb? Okay, so we have a new equation for power, the only equation we have for power, and this question's asking for power. So let's start with that equation. We're going to need to figure out what the work that Dan Osman did is, and we're going to need to know the time it took. Well, we have the time. That's here. But we need it in metric base units. We need it in seconds. And this is kind of a mix of seconds and minutes. So if we take that time that we're given here and we kind of put it in just pure seconds, we say, well, the 25 seconds is fine. I'll leave that. But this 4 minutes, I want to convert that to seconds. So I multiply it by 60. And then I add that to the 25, and I get 265 seconds. So that's the delta T. That's how long it takes Dan to do this rock climb. Now the work he did. If you looked at your formula sheet, you'd see that we've got two equations at this point that have work in them. One's fairly straightforward. It's the first equation we learned in this unit. Work is force times distance. The other one looks a little uglier. It's the one from our last lesson. It's the law of conservation of energy. Both of them have a W in them. Both of these could be used to calculate work. Now, a lot of you right now are probably gravitating towards this one because it's shorter and it looks a lot simpler. But I would warn you that this one is often more difficult to use than this one for these type of power problems that you're going to see in this course. For one thing, this equation has a force in it, and forces can be vectors. And so direction becomes important. And I'm going to need to make sure that that force is parallel to that distance. And a lot of the questions that I'll give you to do with power won't even give you the force. So if you want to use this equation, you might find you then need to go and find the force. And in order to do that, you will need to rely on Newton's laws, and you might feel like it would be really helpful if something was moving at constant velocity, and it won't always necessarily be doing that. So although this equation is nice and short, there's a lot of kind of bumps in the road that you can hit along the way if you're using this equation for some of these power problems. So in a nutshell, this one's hard to use for these power problems, but it does sometimes work. And you might run across some situations where this equation is really your only option. This one, on the other hand, despite looking kind of ugly, is much smoother. This is usually easier to use, and usually for the sort of power problems we're going to get in this course, this is going to be the best way to find your work. So let's tackle this problem. Let's try and find Dan Osman's work, but let's do it using this equation, the law of conservation of energy. So there we have our law. First step, I'm going to fill in anything that I know is 0. And for the things that aren't, I'm going to sub in an equation. So if Dan Osman, I'm going to say initial is him standing at the bottom of this rock wall getting ready to climb it. And final is him standing on top of the wall, having climbed it 4 minutes and 25 seconds later. So initially, he has no kinetic energy. He probably doesn't take a run at the wall. He's probably just sitting there. Initially, he also has no potential energy because he has no height. He's at the bottom of the climb. Then he does some work, right? Gravity will do some work on him. But remember, gravity doesn't count here because we incorporate gravity into this term. And he'll do some work. And so this work other term is the work by things other than gravity, things other than what we have a potential energy term for. So this will be the work kind of done by him. And at the end, at the top of the climb, he doesn't have any kinetic energy. Usually you don't finish a climb still running, still moving. You kind of get to the top and you're stopped. And he'll have some potential energy at the end. And we don't know what that potential energy is, but we can calculate it using our formula for potential energy, mgh. So we basically say here that Dan Osman, at the bottom of this climb, has no energy. He then does some work, and that work goes into giving him potential energy. So this work is basically energy being transferred, as work always is. In this case, it's from Dan's energy stores inside his body. Maybe the sugar from the power bar he just ate. It's going from that form into the form of potential energy by raising him up this wall. So if I get rid of all the zeros, I just find that the work he does is equal to m times g times h. And if I plug in numbers, m, his mass, is 65, little g is 9.8, and his height at the end, remember this height is on the right side of our equation, so it's the final height, is 122 from our problem right here. Multiply those together, and I get 77,714 joules. That is the work that was done on Dan or by Dan to give him this potential energy. So now, remembering we're trying to find the power, we've found the work, we figured out the time right at the beginning here. We can go back to this equation and plug things in. There's my work, 77,714 joules. And here's my time, 265 seconds. Divide them and I get 293.3 for my power. And because I put metric base units in, I know I'm going to get metric base units out. And the metric base units for power are watts. So 293 watts is our final answer. If any of you are sort of high performance athletes and you maybe work in a sport where you calculate your power, it might be interesting to compare this number to what you know you can do. This is actually probably for most athletes who measure their power, this is a really, really low number. And that's because rock climbing is not a high power sport. Maybe for very short intervals of a couple seconds it is, but over the course of a 4-minute climb, these guys are not breathing really hard. They're not straining their muscles. They're working very carefully and very sort of meticulously. So let's look at another example here. A 1,000 kilogram car accelerates from rest to a velocity of 15 meters per second in 4 seconds. Calculate the power output of the engine. So again, power is going to be work divided by change in time. The change in time here is 4 seconds. And the work, again, for most of these power problems, the easiest way to calculate the work is to use the law of conservation of energy. So that's what we're going to do. Let's start out with that law. This car is accelerating from rest. So initially it has no kinetic energy, 0. And there's no mention of any hills anywhere. So we're going to assume this car is just on level ground the entire time. So it has no height. Its potential energy is 0. Then some work is done, right? The car gets some energy from the engine, from the gasoline that the engine is burning. This is sort of energy that's being added to the car. Remember, whenever energy is transferred, that's work. So the car has no energy. It gets some energy in the form of work. And at the end, it has a new amount of energy, which will be in the form of kinetic energy. At the end, this car has some speed, but it still doesn't have any height, no potential energy. It hasn't climbed a hill. It hasn't shot up in the air. So no energy at the beginning, kinetic energy at the end. Where did that energy come from? The work that was done by the engine, converting that energy from the gasoline into this kinetic energy. Now we can put some numbers in. The mass of the car is 1,000. The speed of the car at the end is 15. And if I crunch through that, I get that the work is 112,500 joules. Okay, so now we know the work done by the engine. We know the time over which the engine did that work. We should be able to find the power. So power is work over time. There's the work. There's the time. So the power output of this car's engine is 28,125 watts, or 28 kilowatts. And you'll find often, if anyone here is big on cars, I said power is something that's actually worth bragging about. And if you're looking at really powerful sort of performance cars, because these cars and the owners of them like to brag, one of the numbers you'll always find is the power of the engine. Now, for sort of historical reasons, usually you won't find that power in a number of watts. You'll find it in the units of horsepower. So anyone who's got a big fast car probably can tell you how many horsepower their engine is. But it's actually a quick conversion to go between horsepower and watts if you want to know what that is. Okay, so there is my final answer. Now, because power is not something most of us have a really intuitive understanding of, you guys probably don't really have a sense of how much a watt is or how much 28,000 watts is. I like to encourage students to try and compare it to numbers that they do know. So if you are a bit of a car person and you have a car you like or you have a car you own and you know how many horsepower it is, go on Google, convert that horsepower to watts, and then you get a sense of how many watts of power your car is capable of. And watts will mean a little something more to you then. Also, like I said, if you're a performance athlete, especially if you're a cyclist, you might measure when you're training your power output in watts. There are a lot of devices you can attach to a bike that'll measure your power output for you. And if you're trying to train at a high level, you often want to know how well you're doing. You want to know how impressive you are, what your power output is, how many watts you're exerting while you're riding your bike. So if you happen to be into that and you have one of those devices, you probably know how many watts you're exerting when you're working hard, or how many watts you're outputting when you're just sort of cruising down the street. Keep that number in mind and kind of compare it to the other numbers you get as you go through these problems.